welcome again to Kin 3030 Online, and today we're going to delve deeper into center of gravity. We have talked about it. We talked about it back in the initial kinetics lecture about what gravity is and sort of what center of gravity represents. But today we're going to go a little bit deeper into what that might mean and how you might actually calculate where the center of gravity is in the body, and some applications of why it's important in the biomechanics of human movement. So this will be a problem we will come back to at the end. If you have somebody, they raise their hands up in front of them, what happens to their center of gravity? If you add to them a pie in their hands, what happens to the center of gravity? We'll come back to that. So the center of gravity is a point around which the mass and weight of a body are balanced. If I can get it right. So there's as much, it's not just the amount of mass, but how it's a torque piece. So it's a combination of what the mass is and how far it is from that axis of rotation, that balance point. But that's what balance is. It moves within the body. As we move, it changes its location within the body, and it even can be outside the physical boundaries of a system. So the easiest example of that, of course, is a donut. Nice hole in the middle where air is. That is where the center of gravity of a donut would be, even though it's not inside the body of the donut. And in human movement, when we do certain postures, for example, some piked positions or extreme back extension, you can actually move the center of gravity outside of the physical confines of our body. Center of gravity and center of mass have the same connotation. The gravity is this force. So really, when we're talking center of gravity, we're talking about weight and the balance of weight. Well, the balance of weight and the balance of mass are very similar, but really only has to do with one dimension. That gravity acts down, acts in one direction. We might want to know a center of mass point in the other two directions. Gravity's not acting in those two directions. So that in that case, the center of mass would be a more appropriate term. So let's go back, how they actually calculate or conceptualize this. As I said with the spoon, it's not just that there's an equal amount of mass on either side of that balance point, because that's not what's happening. If you look here, we have a lovely first class lever. We've got the fulcrum, and we have a mass on one side of 60 newtons, and we have a mass on the other side of 15 newtons. Well, if the 15 newton mass was 30 centimeters from the fulcrum, that would create a torque of 4.5 newton meters. If the 60 newton mass, or weight, is 20 centimeters from the fulcrum, that would be 12 newton meters. You've got two torques on either side of that fulcrum created by the weight on either side of that fulcrum, and those torques aren't equal, so it's actually going to tip towards the side that is the 12 Newton meters. There is a resultant moment or a resultant torque. If, however, I shifted the lever over, same length of, same total distance between the small box and the big box, but now the 15 Newton weight is 40 centimeters from the fulcrum, and the 60 Newton weight is 10 centimeters from the fulcrum. In both cases, the torque around that axis of rotation, the fulcrum, created by the boxes, is 6 Newton meters. In other words, it's 6 Newton meters on both sides. There is no resultant torque, no resultant moment or torque. It's 6 one way minus 6 the other way. You add them together, it's going to be 0. That is equilibrium, and that is the center of gravity of that system. So you can find that center of gravity using a fulcrum. In other words, you can find a balance point. You take a system and you find a balance point and hold it there, and that's where the center of gravity is. So somewhere up and down where that hand is, which is the fulcrum, is going to be the center of mass of the chair. However, if we wanted to find the center of mass or center of gravity of a person, a little more challenging, really hard, I've found, to balance a person on the side of your hand. Quite difficult. Also, we're rigid. We are not rigid. We are created with a number of different lengths that can move. And every time we change change into a different posture, we change the overall center of gravity of our whole body. So there's several ways that have been used in the past and currently to find the overall center of gravity of a body or part of the body that we're going to go through. So again, the suspension method would be instead of actually balancing underneath, we would hang from above, and wherever it balances from where we're hanging, it's going to be down below that. Probably a little more apparent with this household item that it's going to be straight down underneath where our fingers are. If you suspend it in two different places on the body, where those cross is where the actual point is that is the center of gravity. You can see hanging it from point 1, hanging it from point 2, and you have the two lines that represent just below the point you held it, and where those cross, that's where the center of gravity would be. The opposite of suspension is balancing, and this is what we talked about earlier, where you have a fulcrum, you have a balance point, you have a board, and you put the person in the posture of interest. You have to remember, you have to put it in the posture of interest. So if you want to know what their posture, what the center of gravity is of a specific posture is, you have to have them on that balance board in that posture. So let's say, I want to know the center of gravity of this posture. I'm going to put this person on that board in this posture and move it back and forth or move the person back and forth until I actually get them balanced. Then I can draw a straight line up. Suspension, we went down. Balance, we go straight up. I then would put them on that board in a different posture. So, for example, I have them turn and do it again, or I have them lie down. and do it again. And so, you know, if I could balance on the here, somewhere immediately above the center of that point, balance point, is where my center of gravity is. Of course, I didn't do a very good job balancing on it, but you get the point. Normally you would do it so there'd be an axis one way, and then you could turn the person and have an axis the other way. Hard to keep putting the people into different postures and having them do that. And it's not very numerical. So the next one is a reaction board that was used. And this was a way to actually find where that center of gravity is. And again, the board acts like a lever. One of the ends is the fulcrum, the end A, and the other one sits on a scale. Nobody has to balance in this one. This is the advantage of this over the balance board. It's very similar to the balance board, but because we have a scale in there, we don't actually have to balance, and you just saw how hard that can be. You have to take into account the weight of the board, and you can either zero it to begin with. There's a question in your book that has it done that way, or you have to subtract out the weight of the board. And then there's a very simple equation that will determine the location of the center of gravity. Oops, coming back to that. So again, we're looking at all the things that go around that fulcrum. Fulcrum is our axis of rotation. So the distance from the fulcrum to where our weight acts, remember, weight acts at the center of gravity. Again, we talked about that at the beginning of the class in third lecture or so. So that distance from the fulcrum to our center of gravity, which is what we want to know, that's the D. We know the distance from, that's going to create a torque one direction. And on the opposite side, we're going to have the whatever force is on the scale times the distance from that fulcrum to where the scale is. And those two will balance out because it's not moving, and we're in a balance situation. So you have torque one way, torque the other way, and that gives you a distance from where that fulcrum is to where the center of gravity of the person is. Now you would have to have them again into whatever posture you would want them to be in. If you want to find it in the center of their body, you probably will have to do it in two different postures so you can get it both in the frontal plane and the sagittal plane. And you have to make sure that you know where the fulcrum is with respect to, let's say, the bottom of their feet. That there's something standard that you're measuring between the fulcrum and a part of their body, so that you then can calculate where that part of the body is to where the center of gravity is. The next one has to do with the finding where, and this is probably the one that's the most important, and that is using the center of gravity of all the different body segments involved, individual body segments, and combining them. We use an electronic location, some film or digital images of the person, and we use known joint locations, bony landmarks, to figure out where the center of gravity of the segment is. And since each body is composed of a number of segments, we can take where each of the individual center of gravities are and combine them all to find the combined center of gravity. So, we have a picture of somebody. Where's the center of gravity of a body segment? Typically, because we can pretty much landmark where our joints are, or most of our bony landmarks are at the joint locations. They're not randomly at that center of gravity. So we need to find a way of estimating that location of the center of gravity of the segment from the joint locations. And the weight of each segment from the joint locations, for that matter, weight of the segment from the whole body weight. So typically we use, again, we put markers onto our bony landmarks joint locations. And from that image, as we can see here, we need to figure out where the center of gravity is. To do that, we use standardized anthropometric data tables. In other words, population data tables. In the past, using various techniques, they have figured out what percentage of a body, one hand, 1 foot, a head is, and for our mass, and they have figured out from our segment length, from a knee to a hip, for example, what percentage of the distance along that segment would be the center of gravity of that segment. What you see here is one of those anthropometric tables. And there are various ones out there. Some are a little more take into account a few more things than others, so some might include separate ones for males and females. We certainly know that although these are median values for the population, different people are made up differently. So we are making an assumption here that we can use sort of median values of the population in order to represent anybody in that population. And there are anthropometric tables that are specific to specific populations. So for example, kids. You might have a table for 10-year-olds or something like that. What you can see here is the various body segments involved. So for example, a thigh and a shank and foot. You can look at just the shank, and which is calf, and just the foot, or you can see shank and foot together. What's not shown here from this table is the next column, which says exactly which bony landmarks are used. So for example, for the thigh, the greater trochanter is used for the hip down to the knee. And the next column, SW divided by TBW. What does that mean? Segment weight divided by total body weight. So it is the fraction of the total body weight that segment represents. So for example, in the thigh, it says 0.1. That means 10% of the body weight in general is one thigh. For the calf and foot, 0.061. 6.1% of the body weight is one calf and thigh. Calf and foot. I apologize. Calf and foot together. The next column, again, a very important column, is the center of gravity CG, divided by the segment length, SL. And then it has brackets proximal. So I have a hip, I have a knee. Along there is my thigh. I know where my hip is. I know where my knee is. I did that by digitizing it or motion capturing it. And somewhere from the proximal end, that's why the proximal is there, you can get a percentage of or a fraction of the distance down that segment that the center of gravity is. So for example, in the thigh, 0.433. If I drew a line from my hip to my knee, 43% of the distance down is going to be from my hip, because that's the proximal end, is going to be where the center of gravity of my thigh is. Now let's think about what that means. If all of our segments were perfect tubes shaped, where would you expect to find the center of gravity? I think you could think it through. The center of gravity would be halfway, 0.5, right? This says 0.433, which means the center of gravity of my thigh is a little closer to my hip than it is to my knee. Well, that makes sense too, because most people's thighs are a little wider up at the hip end than they are down at the knee end, which means there is more mass in the proximal end, and therefore the center of gravity of the thigh is a little closer to the hip than it is to the knee. The last column we will come back to in a future lecture. So continuing on, we know where our hip is, we know where our knee is, we know where our ankle is, we know the mass of the runner. And in both of the cases for the hip, knee, and ankle, we have an X and a Y coordinate. From those tables, we can figure out what the mass fraction of the thigh is, the mass fraction of the shank and foot, the fraction of the segment length from the proximal end to the center of gravity of the segment, which is 0.433 for the thigh, and it is 0.606 for the shank and foot. Now you might be sitting there and thinking, but it's a little thicker up here than it is down here. But remember, the foot's part of this too, and this is where we actually go from knee to ankle, even though it's including the foot. So we have very clear equations. If we want to find the X segment center of gravity equals the X coordinate of the proximal end plus that RP, which we just talked about in the last, that's that location of the center of gravity as a fraction of the segment length, times the X at the distal end minus the X at the proximal end. So you go there and then you add onto it the fraction of this distance. Same thing with Y. So in one case it's the X coordinate, and once it's the Y coordinate. So using that equation for the thigh, we know what our proximal X and Y coordinates are. They represent the hip. Our distal coordinates are our knee. And for our calf and foot, our proximal coordinates are our knee, and our distal coordinates are our ankle. And we can do it in a table is just very helpful in this case, where you look at the X and Y coordinates from the proximal and distal end, and you plug in those using the known fraction, the which is 0.433 for the thigh and 0.606 for the calf and foot. Make sure you know, look at that slide and make sure you know where each of those numbers are coming from so that you can understand what that center of gravity of the segment is. Also, there is the mass fraction. So what is the actual mass of a thigh? What is the actual mass of a calf and foot? Which we use the, again, 10% of the total body mass is the mass of one thigh. So for a 75 kilogram runner, 7.5 kilograms of that runner is one thigh on average. In the end, we get XY coordinates for each of our two segments. This is one of those times where I urge you to take the time and plot it onto the figure. Draw it, make sure that it makes sense. Because clearly, both of those centers of gravities of the segments needs to be on a line between the proximal and distal joints. Using that equation, you will get a center of gravity that is on, if you drew a line from your hip to your knee, your center of gravity of your thigh is going to be on that line. It's not going to be out here, it's not going to be up here, it's going to be on that line. And it's going to be a little closer to the joint that it should be. So in the thigh, 0.433 means that it'll be a little closer to the hip than it is going to be to the knee. For the calf and foot, it's 0.606, which means it's going to be a little bit closer to the ankle than it is to the knee. A little bit, not a lot. There are some body segments where it is actually 0.5. I believe the foot, for example, center of gravity of the foot is basically halfway along the foot between the fifth metatarsal and the ankle. Now we have two body segments and we want to combine them together to get the center of gravity of a leg, because that's really what we wanted to get. So now we have to do what's called a weighted average. So for both the X and the Y separately, we are going to multiply the sum, we are going to multiply each body segment X coordinate with its mass of that segment and add them up. And then we're going to divide it by the total mass of the two segments together, of all the segments if we have more than one segment. In this case it's just two, but so you end up with a weighted average. It would be very similar to finding your grade point average, where you multiply the number of credits a course is worth by what you got on the course, and you divide it by all of the credits you have. And you do that separately for the Y and the X coordinates, and you will end up with a center of gravity location. Now, that center of gravity of that segment, so the whole leg, when you only have two, this doesn't work when you do more than two, but when you only have two segments that are being combined together, you could draw a line between the two center of gravities, and your new center of gravity of your whole leg should be on a line between the center of gravity of the thigh and the center of gravity of your calf and foot, which it is, and it should be a little bit closer to the heavier segment, which in this case is the thigh. So, why is this important in biomechanics? Well, energetically, when we do work, we are going to, we do work on the center of gravity of the system, which would be the center of gravity of the whole body. So when we're walking, of course, our center of gravity of our body is going up and down, so it's pretty important. In the cases of something, for example, quiet standing, and you want to look at balance, you're looking at where the center of gravity of basically, we want to keep the center of gravity of our body over top of our feet. That's a really important concept that we'll talk about in a week or so. But the idea is that your center of gravity, if in quiet standing, would have to be over top of your foot, or else you're going to lose your balance. So in quiet standing, how we keep that center of gravity over top of our foot is really important. Certainly when we do things like ergonomics in lifting, you're going to do a lab, a lifting lab, where you're going to look at somebody who's lifting something, and you're going to need to know where the center of gravity of their upper body is, because if I lift like this, where the center of gravity of my upper body is will very much govern how much muscle activity I need in my low back, which adds to compression in the spine, which adds risk of injury. When you are doing something that is human as a projectile, you're doing a jumping task, it's the center of gravity of our body that is going to follow that projectile path. So by modifying where the center of gravity is within our body, we can actually change where individual body parts are as we go through our path. Can't change where the center of gravity is because it's fixed because in that projectile path, but we can by changing where that center of gravity is in our body. For this is very much a skill acquisition piece. So back to our original problem. Person raises their arms up in front of them. Essentially what's going to happen is their center of gravity is going to go up because there's body parts that have now gone up. The weight of our arms that were down here are now up here, so our center of gravity is going to go up. And our center of gravity is going to go forward because, again, our arms were here. The weight of them moved forward. They moved up and forward. So the center of gravity of our whole body is going to move up and forward. And if you put a pie in the hand, what is it going to do to the person? Well, that's an interesting question. And I'm sure many of you might think, okay, if I put a pie in the hand, it's going to move the center of gravity up even higher because it's still below the arms. And it's going to move it out even further. That is true if you change the system. If you now include the pie into the system. But if you don't include the pie in the system, and you're just looking at the person, in fact, the person's center of gravity doesn't change whether they have a pie in their hand or not. Again, if you include the pie into the system, it will. But if you just say the pie is a force on their hands, it's going to change what they're doing because they now have a force on their hands. It's not going to change what the center of gravity of the person is. So it depends on how you look at it. Nobody likes that answer. So again, we have gone over what the center of gravity is, in particular how it would relate to levers, and some ways, particularly the segmental method for calculating where the center of gravity is of a body segment and then using where the center of gravity is of several segments and combining them to find the center of gravity of a multi-segment body. I mean, that can be expanded to be all the segments of the body, and so that you can get the center of gravity of the whole body.